It is now time for our next presentation on the MegaCast today. Welcome to Rob Girard, Principal Technical Marketing Engineer at VAST, and Howard Marks, Technologist Extraordinary, and I'm not even going to try to pronounce that. Howard is a good friend of ours as well. It's always great to have Howard on, and Rob as well from VAST. Rob and Howard, take it away.
The case for all-flash backup in the age of ransomware is really about the change that ransomware makes in the restore process. In the past, when you did restores, they were almost always on-demand restores because some user or system made a mistake and corrupted or deleted data. And so you were restoring small data sets, a set of files, a VM, maybe a database. And what was important there was how fast the restore started. Since the amount of data was small, how long the total restore took didn't matter all that much. But because by the time you detect a ransomware attack, hundreds of thousands or millions of files are encrypted. Recovering from ransomware means that you have to restore large amounts of data, not a couple of VMs or a user's home directory, but all the user's home directories or all the users whose name starts with A and B's home directory. And this makes life even more difficult because if you write deduplicated data to spinning disks, the spinning disks are essentially having to do random I/O. And spinning disks are not good at random I/O. So the disk that could deliver 125 or 200 megabytes per second of throughput, if you were doing 1 megabyte sequential reads, like everybody thinks backup data is, but deduplication and incremental forever have changed that. If instead you're reading 8K deduplicated blocks, you don't get 100 megabytes per second, you get 800 kilobytes per second. And this just means that restore times suffer. In fact, the vendors of deduplicating disk arrays don't even publish restore performance numbers anymore because a small number of big hard drives has limited their restore performance so much relative to their backup performance. So Rob, why don't you tell it what it is we need for backup in the age of ransomware?
Sure. Thanks, Howard. So I think this slide, we can kind of sum it up here with the characteristics that we're looking for. Now, you can put different labels on this, but I think these categories kind of sum it all up. We're looking for immutability and air gapping. That's that ability to take the tape out of the drive, put it on the shelf where a hacker can't get to it, and change that data. So anything that is offline and couldn't be accessed by a remote attacker, or even better, by a rogue admin. It's off in a safe that they can't get to, or there's a copy there that they can't get to. Instant restores and the ability to restore very quickly. So in that first slide that Howard showed, we have to restore lots of data. We're not going to restore a lot of data if we're trickling that out of storage to put into where it's got to go. We also want to reduce the amount of time it takes to know where our data is good or not. So some of the instant recovery options inside of a lot of the backup vendors is fantastic, but they don't work if your backend's not quick enough to support that. So reducing that time to figure out whether or not your backup's even good or not without having to wait, many, many minutes, hours, days, just to find out that the copy restored is also still bad. Lots of restore points means losing less data. So either going back that much further because you got infected even longer ago than you'd thought and before the trigger hit, or and then minimizing that point to where your data is good and not having to throw a lot out, unless, of course, you just want to pay the ransom. And then detection automated response. So closing down that window to when to detect that there's something gone wrong. And so if we advance here, so now this, back one. Here we go, thanks. So in the age of ransomware, I would say that the last 4 bullets here require all flash storage. So that first one can be accomplished with tape and other technologies, but these last ones really do require all flash for some of the performance reasons that Howard alluded to earlier. Now, the problem with Flash, of course, is it's been too expensive, and and what we've done at Vast is set out to make that not the case, and we've done so in several ways. One is if you can bring more value out of this storage than just backup, so it's not just an insurance policy, but something that can do more for you, such as use some of these detection methods where you need to analyze content in those backups, scan them for something that came out after the fact. So maybe there was something in there that didn't trigger at the time, but later on some virus definitions come out and you need to go back and scan your backups and see if it was ever in there, yes or no. Some of these things mean hitting that data more and more often. And if you're trying to maintain your SLAs of taking new backups, you can't go back and do these things. If you're able to spin up things instantly with instant recovery or leveraging CDP options like continuous data protection to the same box, you need a lot of performance to make sure you can do those things without impacting your ability to keep your backup SLAs. And then, when it's time to restore, where do you restore to? If you can actually use this device, and in the case of Vast, you can, to restore to it, even though that's the home of your backup data, this is an excellent use case where that production array that's gone south, those workloads that are not available due to infection and ransomware. You got to get things up and running, and I don't know many people that are willing to wipe that production array and just go from there. And so in terms of being so that's one way to help the economics of making it too expensive. But then the other is to actually drive that price down. And there's a few ways at Vast that we've done that. One of them is we're using QLC drives. They're denser and cheaper. We're using very highly efficient erasure codes. So that means that our overhead is much, much less than you would find on other systems. So you don't need as much physical flash to provide that usable flash. And then data reduction to stretch that usable flash out to be more and more effective flash. And Howard, maybe you can take us deeper into the data reduction part of that.
Sure, because a lot of people hear data reduction or even hear about the common data reduction techniques like compression and deduplication and think that if a vendor says they do compression or do deduplication, that's all the same. And it's not. There are varying techniques for doing both compression and deduplication. And then we at Vast added a little extra secret sauce with what we call similarity reduction. So compression is a wonderful technique for finding small repetitions in data. It's very fine-grained, but compression generally works over a very limited area. It's very localized. Deduplication finds much larger duplicate strings and eliminates them and uses pointers, and it allows you to reduce data over a larger set of data. But because systems deduplicate on a block size of some amount, that entire block has to be identical. And if one byte is different, deduplication doesn't save you any space. Vast's similarity shares attributes of both compression and deduplication, but it is specifically designed for those cases where blocks aren't identical, where deduplication would reduce them, but are similar, that contain similar data. And so the effect is that we have very wide range of operations. It's global across the entire Vast cluster, but it's very fine-grained. It can find many repetitions of short strings and reduce that data. The combination gives us a level of data reduction that we guarantee is higher than any other storage vendor. But the next question about data reduction is, at what point in the chain do you want to do it? And you have multiple choices. You can reduce at the source, and reducing at the source is good because it reduces the amount of network bandwidth that you use from the client to the backup engine. But because you're reducing using the CPU of a server that you want to actually do real work, that CPU may not be available. You can reduce in the backup server, in the data mover. That's also good for reducing network traffic. It won't reduce network traffic from the client to the data mover, but it will reduce it from the data mover to the storage. The problem here is that deduplication is limited not by being local the way it is on the client, but because backup software vendors just can't make you buy $60,000 servers to run their software. They have constraints on how many cores and how much memory you'll give them. And since deduplication usually requires keeping a hash table in memory, they trade deduplication quality away and deduplicate on large chunks. At the storage, frankly, customers are willing to pay more for that same amount of memory than they would in the data mover because it's hidden in the total cost of the storage system. And so storage systems generally get the best reduction. Storage systems also have more time to do reduction because they don't have to be dealing with it in line. Some processes can happen later. But if you do all of your reduction at the storage system, then you're going to need a big pipe to get to that storage system to meet your backup targets. The things you have to think about are network consumption and the total size of your backup set when it sits in the storage, because that's the storage you're going to pay for. And so you may find that you want to do reduction that's relatively inefficient at the client because it reduces your network traffic by 2 or 3 to 1, and then reduce again at the storage to get another 2 to 3 to 1 and use the least amount of space. So there are other reasons other than just quality that you want deduplication at the storage. And the main one is, as much as you'd like to believe that you back up all of your systems with one backup application, you don't. You change from one version of a backup application to another. You have different platforms you use different backup applications for. Or most commonly, your DBAs don't trust the Veeam or NetBackup or whatever other backup software you're using, and they insist on using RMAN or SQL Server dumps directly to storage. You have a new version of Veeam, it changes the format of the backup. And with all of these software-based deduplication systems, eventually you have some problem with the index that requires you to start with a new full backup. And all of these things add up to mean you get lower and lower reduction and use more storage to hold your backup set, which costs you more money. If you're deduplicating and otherwise reducing in the storage, it doesn't matter that data is coming from multiple streams. If it contains the same data, it's going to deduplicate. And if it contains similar data, it's going to reduce via similarity. So we generally see 2 or 3 to 1 reduction for those cases. So Rob, why don't you tell us about how VAST addresses these issues?
Sure thing. So building on what Howard said about deduplication and storage, it's very important because this is a bit of an insurance policy for you. So if you make one of those changes for performance reasons, and now you need a full copy, that could take a lot of space. So all of these reasons protect you as a customer from not blowing your budget on storage and not going over what you would expect just because you changed a setting inside. So what storage should you choose? Well, I think it's going to be obvious that we're going to say VAST, not only because we work for VAST and we're here representing VAST, but we work for VAST because we believe that we are the superior technology out here for this. So we partner up with all of the modern data protection solutions out there. We're partnered with Veeam and Commvault and Veritas. And we're also partnered with some others that you might not expect so, which are like Cohesi and Rubrik, which, we can provide an archive to extend and take that even further to hold things so that not as many bricks or nodes are required. And so our system is truly built for exabyte scale. So this is one massive namespace that we can keep building upon and building upon. So scale is something that VAST is focused on, and doing so very economically is another thing that VAST is focused on. And then the performance side of it, well, when you throw this many SSDs at something, it's kind of hard to screw it up. So we've put the focus there, and then we've ended up getting excellent performance. It also helps that we did get our start in the HPC space. So I'm not going to say that we ignored performance. That's not at all the case. But our emphasis is really about delivering this all-flash, predictable experience at very large scale. And so some of the ways we can bring down the cost is that effective amount goes that much further with all of the data reduction techniques that Howard just covered. The erasure code. So this is essentially you're taking your disks and you're striping really wide. And on a vast system, on our smallest clusters, our least efficient, we're looking at like about a 15% overhead, which is a 36 plus 4, 36 data and 4 parity. And we can lose up to 4 drives. And as soon as we've lost a drive, we start to rebuild. So we have a failure in place mechanism that will rebuild it. And once it's rebuilt and restriped on the other disks in a very efficient way, where we only need 25% of the other disks to read from to actually rebuild that. And doing it in Flash makes it faster in the first place. Doing so puts us back into that strong state of being able to lose 4 drives again. So and then as this cluster grows and we add more and more of our data D boxes, we call them, our data nodes, that are the boxes that hold all that NVMe and storage class memory. As we grow that, our stripes get wider too and get up to 146 plus 4, which is about a 2.7% overhead. If you contrast that with a shared nothing file system where one node has to replicate to another, and you're automatically using 100% more data overhead just to store that and make sure you're tolerating any failures. So the vast DASE architecture allows for a lot that previous architectures have not allowed for. And then we've battle hardened it with a lot of cyber resiliency features that people are looking for today. So 2 that I want to point out are indestructible snapshots and the policies behind that. So this protects you not only from a rogue actor, but even a rogue admin who has access to the system. So once these indestructible snapshots are created, they cannot be deleted by the admin. There is a support procedure to delete them and open a little window in which configuration can be changed and space can be cleaned up. And then that's closed again. And that is done through 2 people on the customer side, a couple on the VAST side, an exchange of keys, and a process that's longer to explain than we have time to explain it in. We also have S3 object lock, which is the way that most vendors are doing today, so that they're tracking all the versions of what should or should not be there. And if any objects are deleted, those versions are still there and can't be deleted until they expire. So this is yet another way that we can come and help protect this and bring some immutability to a system that is online. Then, of course, we can replicate things and do lots of other stuff there to make sure we've got extra copies and protect those copies as well. And so we support all the leading solutions. And our restores are very, very fast, much faster than you will find from these other vendors that are out there today. So just one more piece on our architecture, if we go on to our next slide here, is the way that we're built with this. Let's see, there we go. So we've got some front end, what we call C nodes. These are running containers, and these are truly stateless, and all of their state is held at the back end. The back end is comprised of storage class memory and very economical QLC drives. Now, we leverage these storage class memory in several ways. One is as a write buffer that has a lot of endurance, and that way we can protect what's generally low write endurance on the QLC. If you don't believe us about the write endurance on the QLC, that's fine. We'll just back that with a guarantee that we will stand behind these drives and make sure they are good for your 10 years of life that we want you to get out of your system. The data reduction, all of the reduction is normally inhibited by how much RAM you have in a system. But in an architecture like this, where we're storing that shared smarts in shared storage class memory, all of those front-end C nodes can take advantage of that. And there's no cache coherency issues or any other issues along those lines. And then from a global data reduction perspective, I can't stress enough how important it is to have it in one big dedupe domain. Because as soon as you outgrow another appliance and have to start a new one beside it, your efficiencies drop a lot, because any new data written to new appliances can no longer be deduped to what had previously been written. And in the backup space, you don't get that space back from what was written before until it ages out, which could be a very long time. So all of these together put VAST as your data protection target of choice. And with that, we're going to wrap it up here and take a few questions.
All right, excellent presentation, Rob and Howard. I always learn so much when you all are on the event. I just brought up a poll question here for everyone out there that says, what additional information would you like about the VAST solution? We do want to get your feedback on this poll. We'll leave it up while we take your questions. So if you have a question, now's the time to get it in. Maybe the first question I should start with is, Howard, what's your title again?
It's Technologist Extraordinary and Plenipotentiary.
Okay, let's talk later about exactly what that means, but I love it. But
it means I got to VAST early and they let me pick my own title.
Very nice, very nice. All right, so back to VAST. First question, I'll go ahead and start with this one. They're asking, won't cheap QLC flash wear out?
So cheap QLC flash actually has interesting endurance characteristics. If you do small random writes to it, it wears out very quickly. But if you do large sequential writes to it, it has over 20 times as much endurance. We don't have time to go into the technical details of why, but the net result is that that same QLC SSD can have very different lifetimes in storage systems that treat it differently. And VAST systems are designed to minimize write amplification, the number of times that data has to be moved, both in the VAST element store in our file system and within the SSD itself. So we write and erase in ways that minimize wear on the flash. And that way we'll write a service contract to replace SSDs that wear out for up to 10 years for a customer.
Wow, very smart. I like that. And another interesting question here. You say storage reduces better. They're asking why.
Why flash storage reduces better? It's not that data reduces better on flash storage. It's that flash storage maintains its performance when delivering reduced data. Data deduplication is where a lot of the reduction in most systems comes from. And data deduplication takes a large sequential write, like a backup stream, and breaks it up into blocks. And if some of those blocks are copies of existing blocks, it just uses pointers. That means when you do a large sequential read, instead of it being a large sequential read on the hard drives in the back end, the system has to rehydrate the data. It has to reassemble all of those blocks into the file that you asked for. And that means that it's doing a lot of random I/O on the hard drives. And hard drives don't do random I/O well. One hard disk will do about 100 IOPS. One SSD will do about 100,000 IOPS. And so if you deduplicate to spinning disk, your read performance for large reads, like the restores you have to do when you're struck with ransomware, become much slower. Our system, because it's based on flash, is slower to write data than to read data back from. So as long as you're backing up fast enough, your restores are going to take less time than your backups, as long as your target system can ingest data that fast.
Very nice. Let's see. Good question here from Heath related to flash. He's asking, how do you see flash storage technology improving in the future?
Well, we've already seen one of the vendors we buy SSDs from, Solidigm, announce 60 terabyte SSDs and PLC flash. So QLC flash is 5 bits per cell. QLC flash is 4 bits per cell. PLC flash is penta-level cell. It's 5 bits per cell. gets about 25% more bit density for the same production cost and the same amount of space. So we're going to see the cost continue to come down, the density continue to improve. And really, cost is the only advantage that hard drives have over SSDs today. There's no reason to buy a hard drive except that it's cheaper than an SSD of equivalent capacity.
Wow, that's amazing. It's just incredible numbers there. Another question they're asking if VAST integrates with public cloud storage in some way.
So today we essentially back up to an S3 compatible object store, which could be a public cloud object store. And so we'll take a periodic snapshot, bundle the changes since the last snapshot into self-describing large objects that we write to the object store that you can then restore from. That's not a great solution for the kind of restores we've been talking about today, because your link to the public cloud becomes the performance bottleneck on restores. But it's good for the cold data you don't plan to ever access, or that you plan to access very rarely.
Right. Okay. Got it. Let's see. I think that's all the questions I see here at this point. But I do want to ask you a question. What's the best way to get started with VAST and to learn more?
Well, I'm kind of biased. If you go to vastdata.com/whitepaper, you'll find our architecture white paper that I wrote. And so I would generally send you there.
Excellent. Howard, it's always good to have you on. Always good to chat with you again. Thank you so much.
Always a pleasure.
Really cool presentation, cool solution from VAST. So take care, and we'll see you next time.
Thank you.